Hello everyone, welcome to CPRICT. In this video, we are going to look at the first 4 problems from the recent Codeforces educational round 97. So let's get started. The problem A is called marketing scheme. The real problem statement starts from this paragraph I guess. What it says is, if a customer wants to buy X number of cans from a shopkeeper and we need to choose a particular number A such that X mod A becomes greater than or equal to A by 2, and if this condition is met, then the customer will be buying the whole pack of A cans instead of buying X mod A cans. And our customers can the customers that come to our shop can buy any number of cans ranging from L to R inclusive. We need to find out a number A such that this condition is met for all the numbers which lies inside this range, which is L to R. So let's see what we can do to solve this problem. So X mod A should be greater than or equal to A by 2 for all the numbers ranging in between L to R. Now let's take the number L, which is the smallest in this range. For this L, the maximum A we can choose would be 2 into L. For 2 into L, suppose if A is 2L, then X mod A would be L mod 2L, which is equal to L, and it itself is equal to A by 2. In that case, our customer will be buying a whole pack of cans which includes 2 into L cans. Now this condition should be met for all the numbers ranging from L to R, and we have found the maximum number we can use for this, the smallest number R. So this condition should be met also for the largest number in a range, which is L. So the largest number R should be less than or equal to 2 into L. If this is the case, then we are sure that for all the numbers our X mod A would be greater than or equal to A by 2. But let's say if our R becomes greater than or equal to 2 into L, then there would be there is one number where R is equal to 2L. In that case, if we do X mod A, then it would be equal to 2L mod 2L, which is equal to 0. And if as it is less than A by 2, in that case our customer will be buying 0 cans from us, but we do not want this situation to occur. So the code is simple. Let's see the code now. It is as simple as this. If R is less than or equal to 2 into R, we print yes, otherwise we print no. Now let's see the second problem B, which is called reverse binary strings. We have been given a string S of even length n, and S has exactly n by 2 zeros and n by 2 ones. In one operations, we can reverse any substring of S. Substring, this is the definition of substring. We need to find out the minimum number of operations to make string S alternating. By alternating, it means that it should consist the numbers in the way 0 1 0 0 1 or 1 0 1 0. In other words, Si should not be equal to Si plus 1 for all the i's. Let's see what we can do to solve this problem. So we have been given a binary string. Let's consider the last example which they have given, 1110 1000. Now let's consider all the pairs of characters which are equal. Suppose all the pairs where the adjacent characters are equal. Now I would be counting such pairs for the character 1, and I will be storing the number in count 1, and I would be doing the same for character 0. I would be storing it in count 0. Count 1 stores the number of pairs where the characters are adjacent as well as they are equal, and if they are both are 1, I am just incrementing this count 1 variable, and if the adjacent characters are equal and they both are 0, then I'm incrementing this count 0. I'm incrementing count 1 when the adjacent characters are both 1s. And the answer would be the maximum of count 1 or count 2. Why is it so? Let's try to analyze this. Now what we can do, we can reverse any substring of our main string in one operation. Whenever we see there is a consecutive set of characters which are equal in one operation, we can remove these such number of pairs by one only. For example, let's say at this moment we have three pairs of ones, and yeah, let's say we have three pairs of one. So if I try to reverse any substring in one operation, I can remove at most one pair. That is, if we consider this example, I see there are 1, 2. There are only two pairs where when I see the adjacent characters are equal and they are 1. If I reverse any substring in one operation, I can reduce this number of pairs by one only. So how I can do this? First, I can reverse this substring. Now it will become 1 0 1 0 1 1 0 0. Then you see that in this string I have only one pair of ones which are adjacent as well. But here it was 2. And to make this into an alternating string, what I can do is I can simply reverse this substring. Then it will become 1 0 1 0 1 0. Now this is for the case when I am reducing the number of pairs of ones, but there can also be other cases when I want to reduce the number of adjacent zeros. Let's see one example. This is one example. Here if I see the number of pairs of ones which are adjacent is 0, but for the character 0 I have one pair where the characters are adjacent and they are equal as well. So I need to reduce these pairs, and I can do this by using one operation. I can simply reverse this substring, then it will become 1 0 1 0. And in other example, in this case I see the number of pairs of ones is 1, but for 0 there are no such pairs where the characters are same and they are adjacent as well, they are zeros. In this case I can simply reverse either this substring or I can reverse this substring. After reversing it, it will become 0 1 0 1 if I reverse this one. So that's all for this problem. Let's see the code now. So I've maintained these two variables. I'm iterating my whole string. If I see the adjacent characters are equal and they both are 1, I'm incrementing count 1. If they both are equal and they are 0, I'm incrementing count 2. At the end, I'm just printing out the max of count 1 or count 2. Now let's look at the third problem, which is C, chef Monocarp. We have n dishes in an oven, and the chef, he knows that ith dish has optimal cooking time equal to ti minutes. So if I let's read out the problem statement. At any positive integer minute t, capital T, Monocarp can put no more than one dish out of the oven. So at any instant of time, any integer instant of time, I can move out at most one dish out of the oven. If the ith dish is put out at some time t, then its unpleasant value is the mode of the difference between t and the ti, which is equal to the optimal cooking time of the ith dish. If the dish is out, it cannot go back in. It should Monocarp should put all the dishes out of the oven. What is the minimum total unpleasant value Monocarp can obtain? And we see the range of n is pretty less and cannot exceed 200. It is a classic dynamic programming problem. Let's see how it can be solved. So I'm seeing that n is less than equal to 200. And one more thing here is the values of ti's ranges from 1 to n. So ti would be 1 to n. What I would be doing is I will build a recursive function. Let's call it sol, and first it would be the idx. It means the index of the element I'm considering at this moment. So I have an array of TIs, the array of optimal cooking time of my dishes. So index represent the index I'm currently at, and the next variable would be the current time. This is the current time which I am at, and the value of T would be starting from 1. This the time I am moving up the dishes, and it can go like, we do not need to go further 2 into n. Why 2 into n? Because let's say I have 5 dishes and the optimal cooking time of all of those are 5, and I can start my cooking time from 1. For this it would be 1 2 3 4 5. But also, if suppose my cooking time was 5 5 5 5, in that case what I can do is I can simply put my cooking time as 3 4 5 6 7, I guess. Yes, it would be the optimal time. I guess I'm right. So it cannot, the time which I need for the dish which has the highest optimal cooking time would not exceed 2 into n. First I would be sorting my array. First I'll sort the cooking times of all the dishes. For the last dish which is having the highest optimal cooking time, the time which I would be moving out that particular dish would not go beyond 2 into n. So I can simply create a DP where the first state would be the index of my array, and the second would be the current time, and it ranges to 2 into n, and this is n, and as n is 200, it is pretty space efficient. We can solve this problem. Now let's see how we can solve this. So if we see that, and if we are using zero based indexing of our array, so if we see our idx is equal to n, that is we have traversed our entire array, that is we have seen all the dishes, simply return 0. And if we see the idx is less than equal to n, idx is less than n, not equal to, and the time has reached to 2 into n, so we will simply return a value which is maximum, that it will just tell us that this is not the solution we are looking for. We'll simply return 10 to the power 8. It will nullify all the results which we have gathered till this point. So if we have reached to this point, what I'm saying is I do not want to consider this particular recursive call. It will not give me the optimal answer. And if I see I have the value for this particular state in my DP array, I'll simply return it. And for any time t, and for any dish, for a dish present at index idx, I have two choices. Either I can move it out, or I can just simply let it be and move ahead with my time by 1. Let it be. If I'm moving out my dish at this moment, so I need to add absolute difference of ti minus t, and then I'll call the recursive function on the further dishes of my array, idx plus 1 t plus 1. And if I'm not moving out the current dish at this moment, I'll simply call my new recursive call on the same index, but the time would be increased by 1. Let's see the code now. It is pretty small as well, I guess. Yeah, so I've read the input. I've initialized my dp2 -1. I've sorted the optimal cooking times of my array. Then I've called the function on the 0th index, and initially the value of the current time is 1. Now let's see the recursive function. If I see after the whole array, I'm simply returning 0. If time is equal to 2n plus 1, I'm returning a value which is very large, such that it will nullify all the results which I have gathered till this point, because I just need to make sure that it will tell me that this is not the optimal solution. So I'm returning this value at this point. If I've already calculated the answer for my DP, I'm returning it. Otherwise, I have two choices. I do not move out the current dish at this moment, so I remain at index idx, but the time is incremented by 1. Otherwise I can move out the current dish, so I need to add absolute difference of this, and I would be moving further ahead in my recursive calls. I call on it on the next dish which is present at the index idx plus 1, and time will be incremented by 1 as well. At the end I'm returning the answer. That's all for this problem. Now let's look at the next problem. The problem D is called minimal height tree. So the Monocarp guy has performed a BFS on some tree, and the way he has performed the BFS is as follows. The order in which he is traversing the nodes, it is stored in the array A, and he's using a Q. Initially he starts from the root. The root is at the node 1. What he does is he pop out one element from the queue. He append it on the list of the nodes which he is visiting on his BFS. Then he checks all the adjacent nodes of this current node, and GK is the list of all the children of vertex K sorted in ascending order. So this is an important thing which we need to consider when we are solving the problem. So the way it is moving out its children is the children are in increasing ascending order. Children basically. Monocarp has fascinated by BFS so much, but he has lost the tree. He does not have the tree right now, but he still has the array A which stores the order in which he traversed that particular tree. We need to find out any tree which satisfies this BFS, and we need to find out the tree which has the minimum height. See, there can be multiple trees which would be satisfying this particular BFS. We need to find out, and also there can be multiple multiple trees which has the minimum height. We need to find out only one, and at the end we just need to print the minimum height of that particular tree. Let's see how we can solve this problem. So we have an array A. Let's take one example. Let's take the first one. We have 4 nodes, and BFS sequence is given as 1 4 3 2. I think this is not the right example. Let's say I'm using the example 3 4 5 2. I guess this might help. So we have this BFS which Monocarp performed initially. We need to find out a tree, so we would be using a queue. Initially we are sure that he must have put the root of the tree in his queue as he performed the queue BFS. So this is 1. So at this point our queue is containing 1. We will run a while loop till the queue is not empty. So we do like till queue is not empty. We'll keep on what we're doing. We'll pop one element from our queue. So at this moment it would be 1. So we attach, let's say we are drawing this one as well. Now what we would be doing, we are also maintaining index idx which tells us at what index we are currently at. We are currently looking at, or the starting node which we have not inserted in our queue yet. We have already inserted the root of our tree, so at this point index is pointing to this element which is 3. Now as a particular node can have any number of children, and we need to put as many children we can because we want the minimum height of our tree. And the way the Monocarp popped or checked all the children is they were pushed, or they were stored in increasing order. So we will be going as far as we can till the increasing order is maintained. We see 3 4 is greater than 3. Okay, so first of all what we do, we attach 3 to this. We check the next node which is 4. Now idx pointing to this. 4 is greater than 3, so we also attach 4 to this. Now we move to this 5. We see 5 is greater than 4, so we can attach 5 as well. Now we move to 2, but we see 2 is less than 5. So Monocarp cannot put of 2 here, which the 2 cannot be a child of 1, because as the children were in increasing order, which are 3, 4, 5. So 2 cannot be a child of 1. Now we have, and the time at which we were moving ahead in this traversal, like when we were incrementing IDX, we also pushed these elements in our queue as well. So initially 1 was in our queue, we popped it, so 1 is not there at this moment. Then we pushed 3, we pushed 4, and then we pushed 5. So, and at this point we cannot push 2 into it, so we pop one element from our queue, which is 3. So now our current node is 3. Now we check, yeah, anyway the first we can always attach one child to any node. So 2 is the first, 2 can be the first child of 3, we can anyway attach it. We have reached to the end of our array, so this would be the minimum height would be 2. Let's take one more example. Yeah, let's take this example. So at this moment I'll start my BFS from this. So my queue is containing 1. I pop this 1. So let's draw the tree as well. So 1 is there, index is incrementing by 1 as well. Now we try to move as far we can till the increasing order property is maintained. So we can go at most till this point because 3 is less than 7. So we attached all these 3 points, all these 3 nodes as the children of 1. So 5, 6, 7, because these are increasing order. Now we have popped this 1 from our queue, and we popped 1 and we pushed 5, 6, and 7. Now we pop 5 and we see our index is currently pointing to 3. Now again we try to move as far as we can till this increasing order property is maintained. We can go till this point. We want to put as many children as we can. So we can go till this point. We'll simply attach 3 and 4 as the children of 5. Now 5, we're done with 5. We pushed 3 and 4 in our queue. Now we pop 6. We check this, and we, as already mentioned, that we can always put one children to any node. So 2 would be the child of 6, and we have reached to the end of array. We see that the height of this tree is 2. Simply return 2 after that. Let's see the code now. Yeah, this is the D which I have initialized to 0 in the beginning. This would be the minimum height of our tree. IDX is the index of the node I would be considering next. I push the root into my queue. This count tells me the number of nodes I am having in a particular level. Initially, when I had pushed the root into my queue, at that moment the level 0 contain only one element, so I initialize this count by 1. And x, I'm using x to find out the number of nodes in the next level. The time at which I'm popping these 5, 6, 7 or pushing 5, 6, 7 and 3, 4, I am just implementing x as well to find out the number of elements I would be having in the next level. Initially, as I would be finding the number of nodes in the next level, so I initialize it to 0. I pop all the nodes of my current level, and my current level is containing count number of nodes as I've mentioned. So I do this count number of times, like I do all of this count number of times. I pop the element. I set previous as -1. Previous basically stores the value of my current node, and as I had mentioned that we can always push one child into my as I can attach one child to my current node. So initially I am initializing this previous by -1. I try to move as far as I can till the increasing order property is maintained. I check whether the current value is less than previous or not. If it is less than previous, I cannot go beyond. I simply break out of the loop. Otherwise, I update my previous. I push that particular node into my queue, and I increment IDX as well as X. This X will be helpful when I would be calculating the number of nodes in my next level. Yeah, so here I am just updating count, which I would be doing in the next iteration. And if I see I still have some elements in my queue, it means I would be doing this processing, this whole process once again for the next level. If still I am left with even one element in my queue, I'd be doing all this for the next level. That is why if I see that queue is containing even one element, I increment d++. So, and I will break out of the loop when my queue is containing 0 elements. At the end, I'm just printing out the answer. So that's all for this video, guys. I hope you liked it or learned something from it. If you did, please hit the like button, share it with your friends, and consider subscribing to our channel. I'll see you next time. Maybe we'll solve few problems of this contest, maybe E and F, I guess. Till then, take care, sayonara, happy coding.